Hi everyone. So I wanted to film a short video and tell you about a concept that you might encounter in the future. You won't need it in this class, but I think it would be dishonest uh, to introduce you to quantum mechanics without mentioning something called quantum coherent states. Because the presentation in introductory, when quantum mechanics is introduced, the presentation of wave-particle duality causes some students to ask questions like, what can I do in order to go through a wall, or something like this? What can I do in order to feel like a wave, or something like that? So these questions are usually caused by the discussion of wave-particle duality, that sometimes particles act like waves, sometimes they act like they exhibit more particle-like behavior. And so naturally these questions arise. But that's not the whole story. There's another part of the story that you're not told, and the textbook doesn't tell you. And so I wanted to say just a few words about that. But before that, I want to review that we saw that entities, let's say call them particles, behave like waves or behave more like particles depending on the context, right? So we've seen this context dependence, right? One example is when I talked about diffraction of particles through slits or through double slits, that when the wavelength is comparable much or larger than the slits than the aperture, then the diffraction is strong. So it's clearly a wave behavior. On the other hand, when the wavelength is much less, when the de Broglie wavelength is much less, then the geometry of whatever the particle is moving through, then the wave behavior is not as strong, it's not as manifested. So that's one example of context dependence. Another example is in analyzing whether the uncertainty principle is relevant, right? The uncertainty principle is inherently a wave principle, right? We saw from the wave lab where the uncertainty principle really comes from. And so it's a wave effect. And we saw that in some cases, uncertainty principle poses a very significant restriction. So for example, we saw that the uncertainty of electrons' momentum inside an atom is comparable to the momentum itself. So clearly it's important. Whereas when we looked at the dust particle, we saw that the uncertainty in momentum is, I forgot, it was something like 10 to the minus 26. And the question is, do we care about this 10 to the minus 26? Or can we essentially say that there is no uncertainty? Okay, and in that case, what we want to compare that fundamental uncertainty with is with the experimental uncertainty, right? So if I have some kind of a, let's say that this is a number line, and this is some numbers. Let's say this is a 0, and this is some number. Let's say position of something. I can never measure position precisely, right? There's always uncertainty. And so let's say the experimental uncertainty is this much, right? So if a million people measure position, they would get values with standard deviation, say this big, right? It would be some kind of a distribution. Some would get outside, but that's an experimental uncertainty. And so when the theoretical or when the uncertainty imposed by the Heisenberg principle is less than this, I wouldn't care about it because the uncertainty from experiment is large. On the other hand, if the uncertainty from experiment is much smaller and the Heisenberg uncertainty is larger than that, then I would care about the limit imposed by the Heisenberg uncertainty principle, which is fundamentally a wave effect. So this is yet another example where waviness or wave of where the wave nature of an entity whether that wave nature of an entity is expressed or it's irrelevant, where that depends on the context. Okay, there's another example, right? So I guess I didn't talk about it. It's something called particles in a cloud chamber. So the way that particles were originally detected in the early 20th century, like electrons, protons, neutrons, mesons, and so on, they were sent through cloud chamber. And when a particle goes through a cloud chamber, it ionizes atoms in the vapor. It's, for example, alcohol atoms. And that creates a little bubble or a little trace of cloud, and so you could visualize the particle. And when you do that, you can kind of see a particle streaking through, and you would say, wait a second, that looks like a trajectory to me. You told me there's no such thing as trajectories. But the reason that this looks like a trajectory is because this method of measurement, the method of visualization by nucleating clouds, is a very crude, it's not a very precise method of identifying positions. So really it's the delta X is quite large. And so delta P is not too large. But if we were to measure, right, so you get sort of this particles of droplets of bubbles, and it looks like it's a trajectory, right? It looks like it's a classical idea, but I told you that trajectories don't exist in quantum mechanics. The other, but if we were to try to measure positions more precisely, right? If we were to minimize delta X, right? So that increases delta P. And when delta P increases, that means the wave function of the particle has more and more wave number components. And if it has more and more wave number components, right, we discussed what happens to, so if the Fourier transform goes from being something like this to being something like this, right? So delta X is smaller, delta P is larger, Fourier transform is broader. And when the Fourier transform is broader, you have broader set of frequency components, or wave number components that enter the wave function. And that wave function falls apart quicker, okay? It doesn't keep its shape for very long. And what that means is that when you do perform a measurement of position very precisely, the momentum is very uncertain. And so the next measurement of position, when you try to measure position of the particle at the next instant of time, you would get a value here, and then maybe value here, and the value here. And so the more precisely you try to measure the position of the particle, the more jagged and irregular the trajectory becomes. And if you were to try to measure the position of the particle at smaller time intervals, then you would get kind of almost a fractal type pattern. It would not be a trajectory. So this is, again, an example where whether the particle behaves like a classical pebble, or whether its wave properties become manifested, that depends on the context. So this is all well and good. However, there is another part of the story. And that other part of the story is, I think I should just tell you, for cultural reasons, you will not need this in this class. So if you want, you can skip the rest of this part of the lecture, but I would feel guilty not telling you about this. And this is called quantum coherence. It would be dishonest to present a modern introduction to quantum mechanics without even mentioning this. So what is quantum coherence? So you might be clever, you might say, well, if every atom in my body, or if every electron in my body clearly acts, its wave properties are clearly important, right? Clearly, maybe even the nuclei, their wave properties are important. So if I put them together, how come as a whole, my wave properties as a macroscopic being are not really important? You said, okay, fine, it depends on the context. Well, the electrons in the atoms, in that context, their wave nature is clearly important. Later maybe we'll talk a little bit about atoms. We'll talk about this 3D probability cloud that you learn in high school. That's all very much a wave effect, right? So the probability clouds are solutions to the Schrodinger's equation, which is a wave type equation. That's a very wave effect. And you might say, well, if every electron in my body acts like a wave, it has nodes and antinodes and so on, then why I as a whole don't act like a wave? That's a very interesting question. And so now I would have to give you an analogy, just an analogy. imagine there's a stadium of people. Okay, and imagine if every person, or a concert, imagine if every person is doing this, like waving their hands. If everyone is doing this incoherently, out of sync with each other, then when you look at the whole stadium, you will not see any kind of a wave behavior. But if every person in the stadium or the concert venue was doing this coherently, in phase, they don't have to go all in phase. There could be kind of a gradual phase relationship from one seat to the next seat. But the point is, there has to be some kind of a non-random phase relationship from one person to the other person. Then you would see a wave of hands moving through the stadium. And if the phase from one person to the other person is zero, if everybody is doing this in the same phase, then the whole stadium would do this together. And if there was a phase relationship from one seat to the next seat, then there would be a wave of hand motion kind of rolling around the stadium. The point is, this second case is an example of coherence. It's an example of quantum coherence. Oh, sorry, coherence, not quantum. So this is the analogy for what, this is the analogy for something called quantum coherence. So when particles act like waves, when you put them together and form a macroscopic object, the object generally does not retain the wave properties, even if individual constituents clearly have a non-ignorable wave behavior. And the reason for that is a loss of coherence. There are some exotic examples where that coherence is not lost. One of them is superconductivity. So generally, electrons move through solid incoherently. The wave function of one electron is one thing, and the wave function of another electron is its own thing. They're not in sync. Their waves are not in sync. That's what I mean. And so, but there are situations when the wave functions of all electrons are coherent, when they're in sync. And when that happens, you get something called superconductivity. And there are lots of interesting symptoms of superconductivity. One of them is the loss of resistance, but it's not the only thing. Superconductors are not just zero resistance materials. They have a very interesting response to magnetic fields and so on. So another example is something called a superfluidity, superfluid. That's another quantum coherent state in which all constituent particles enter this coherent state, like the people in the stadium. And part of the reason I wanted to mention this is that quantum coherence is a very important issue in building quantum computers. The reason it's so difficult to build quantum computers is that if you want more than just several qubits in a quantum computer, those qubits have to be coherent with each other. So a qubit is a unit of quantum bit, and what's a qubit in practice depends on the quantum computer. In some cases it's electrons, in some cases it's ions, in some cases it's magnetic spins, a unit of magnetism basically. And if you want them to be, if you want a truly quantum computer, these qubits, if you want more than just a few qubits, they have to be in a quantum coherent state. Why is it so hard to have a quantum coherent state? Like, what's destroying the quantum coherent state? And the answer is interaction with the environment. So I guess maybe I can try to go back to the analogy with the stadium. If everybody's doing this, but every person starts getting distracted, you lose the quantum coherence. So if you have a bunch of atoms that are in a quantum coherent state, but they're not in a vacuum, they're interacting with the environment. And that interaction with the environment causes the quantum coherent state to disappear. And so whenever you're tempted to ask, like, what can I do to diffract through a wall or to diffract through a keyhole or something like that? Well, first you have to be in a quantum coherent state in order to do that. That's really what's necessary, and that's really hard to do. It's very, so far, I don't think our macroscopic objects have been put into a quantum coherent state. One example that people are trying to do is they're trying to put LIGO mirrors into quantum coherent state. LIGO, gravitational wave detectors. You might say, what? Why LIGO mirrors? Like, why? Well, LIGO mirrors are very massive objects, but they are isolated from the environment. Why? Well, to minimize their vibrations, to minimize the noise. And so also they're cooled down. And again, they're cooled down in order to minimize the influence of the environment. And so they're cooled down, they're isolated from the environment, and that's a perfect scenario for trying to achieve quantum coherent state of a 1-ton object. They're very heavy, very large macroscopic mirrors. As far as I know, that has not been achieved yet, but people are trying to do. And it would be really interesting to put a large object like a 1-ton mirror into a quantum coherent state. The point is that these are all very up-to-date issues. If you're a physics major, if you're an electrical engineer, you might encounter this. And one way in which you would encounter this is in quantum computing, but not just in quantum computing. So quantum coherence is a very interesting sort of modern subject. People are trying to put macroscopic objects into quantum coherent states. And I just wanted, if anything, I just wanted you to know this word combination so that you will keep this in the back of the mind, right? That's really another part of the story. So it's not just wavelength versus the size of the apparatus. It's not just the Heisenberg uncertainty principle, it's quantum coherence. And the process by which coherence is lost is called decoherence. And so, for example, in discussing whether something is quantum coherent or not, people talk about something like something called decoherence time. And the decoherence time decoherence time depends on the interaction with the environment. Usually the interaction with the environment is what causes decoherence time to be very small. So even if something was quantum coherent, it quickly decoheres, and then the macroscopic object loses wave behavior. It begins to act like a classical particle, classical object. The discussion of classical to quantum transition is a very deep one. It's a very mature discussion. You have to go to graduate school for that to really understand it. It's not just a matter of learning about Heisenberg uncertainty principle and waving your hands around. I just wanted wanted you to understand that when you're tempted to ask questions about diffracting through keyholes and things like that, there's a lot going on. It's not just a simple thing that you learn from chapter 3 or chapter 4 of this book. Okay, so this is mostly for your culture. I'm not going to test you. I'm not going to ask you questions about quantum coherence. This is just to be a more enriched, to be a more enriched student in the introductory quantum mechanics rather than just the standard material. Okay, well, thank you.